Alrighty, folks, today we are going to be talking about magnetic domains. Alright, so let's go ahead and start off by getting your notes set up. Our essential question for today is what makes a material magnetic? Our four guiding questions are, how do electrons relate to magnetism? What needs to happen on an atomic level for a material to be magnetic? What materials can be magnetized, and how do you magnetize a ferromagnetic material? Go ahead and pause the video, set up your notes, and then we will continue. Our learning target for today is I can explain why some materials are magnetic and others are not. Alright, let's start off on the most base level, and that is what is called electron spin. So, electrons orbit the nucleus of an atom. They are also, in addition to that movement, rotating or spinning. Well, as we are going to learn later on when we talk about electromagnets, charge, anything that is charged, so electrons have a negative charge, plus them being in orbit, plus them having spin or rotation, causes them to become tiny magnets. So, electrons occur mostly in pairs, and these pairs have opposite spins. So, opposite spin electrons cancel out each other's magnetic effects. So, in general, they are going, or when electrons are paired together, there's going to be no overall magnetism. Most materials have most of the electrons paired up, and therefore they have very weak magnetic fields. So as we said, most materials are not magnetic, but what about unpaired electrons? So, unpaired electrons produce magnetic fields. Usually, when materials have one or more unpaired electrons, their atoms' fields don't line up, and this makes an overall weak magnetic field. So they're all pointing in different directions, and so the magnetic fields aren't very strong. However, if you get a bunch of atoms' magnetic fields to align, that creates what is called a magnetic domain. And a magnetic domain is a region that has a very strong number of atoms with aligned magnetic fields. And magnetic domains have strong magnetic fields because the atoms' magnetic fields are aligned. So over here, I have this little animation of some ants. So I want you to think about it like this. If you have a single ant is like a single atom with an unpaired electron. It has a magnetic field, and a single ant has some strength. So like a single ant could pick up maybe like a grain of rice or something. An atom with a magnetic field, an unpaired electron and a magnetic field, it has some magnetism, but it's pretty weak. However, if you get a bunch of ants all working together in the same direction, their strength increases a lot. And so if you get a bunch of ants working together, they could pick up maybe like a whole grape or something, which is way stronger than what a single ant can do because they're coordinating their strength. The same thing is true of atoms with unpaired electrons and magnetic fields. If you align all those magnetic fields, all of a sudden, the combined magnetic field is much, much stronger than the sum of its parts. So that's why I kind of like to think of magnetic domains as ants all working together. So if you look at a magnetic material and you zoom in with it really closely with a microscope, you can actually see the magnetic domains form. So this right here, I believe this is some iron, and you can actually see right here, this is a magnetic domain. And you can see all the different magnetic domains and how they kind of have different alignments to them. And so this is a real thing that we can look and directly see the results of magnetic domains. All right, so ferromagnetic materials. So what materials can be magnetic? Well, materials like iron, nickel, and cobalt have enough unpaired electrons, and those atoms make magnetic domains by aligning. And so, a ferromagnetic material, a material such as iron, that can be magnetized because it contains magnetic domains. So, let's take a look here. Right here, we're looking at imagining a piece of iron with all these different magnetic domains. And you can see here that all of the magnetic domains, their magnetic fields are pointing in different directions. They're all over the place, so they're random. So each of these magnetic domains, their north and south, are pointing in weird directions. And therefore, they don't coordinate with each other and don't make a stronger magnetic field. And so this would be an unmagnetized piece of iron. So just everyday nail or something like that, that's not going to attract other pieces of iron or other pieces of metal. However, if you take all of the magnetic domains or the vast majority of them and align them with each other like we have in this image, then that is going to be a magnetized material. And we are going to talk in our next lesson how you go about making a material go from this unaligned magnetic domains to aligned magnetic domains that are magnetized. So, magnetization. If a non-magnetized ferromagnetic material is placed in a magnetic field, it will cause the domains to align. And as I said, we're going to show you some examples of that in our next lesson. So, you can see here we have our random magnetic domains in a piece of iron, for example. And then you place them in a strong external magnetic field. All that means is that you're placing a strong magnet next to a piece of metal. And that is going to cause all of the magnetic domains to align with the magnetic field of the magnet next to it. So this would then become a magnet. So because atoms are in constant motion, these domains are going to become disorganized after time, and the magnetization is lost. And so, if you use a weak magnetic field, so like let's say that you were just using a little refrigerator magnet, yes, you can briefly make something magnetic, but it's not going to last very long. But if you were to use and so as a result, the magnetic fields are going to, or the magnetic domains are going to revert more to a random, and it's not going to stay magnetic very long. However, if you use like a really strong electromagnet, you would magnetize these fields and align them, and they would stay aligned for quite a long time and become a quote-unquote permanent magnet. However, there's no such thing as permanent magnets because over time, even the strongest magnet will ultimately degrade. All right. So I want you to turn to your bar magnet diagram, and you should have a magnetic field added to this at this point. I would like you to go ahead and add to this the magnetic domains. Remember, magnetic domains point from the South Pole to the North Pole when they are aligned. So go ahead and add your magnetic domains to your bar magnet diagram. In the next, I have a video coming up here to kind of explain what happens when you break a bar magnet in half and what happens to magnetization, and you'll see what a diagram of a bar magnet with magnetic domains looks like. Alrighty, folks. Let's go ahead and take a moment now to think about what would happen if you break a magnet in half. So I've got a magnet right here, and I have it represented on the whiteboard right here as filled with magnetic domains. All of those magnetic domains are aligned from the South Pole to the North Pole so that we have our two poles. And if you use a bar magnet, you would see that's the case. But if we were to go ahead and split this magnet in half, we would now see that all that happens is we broke it in half here, and now this part, the magnetic domains are still aligned, and this part down here, they're still aligned. So what happens now is that this is the South Pole of this magnet, and now this is the North Pole of this magnet. On this magnet here, this is the South Pole, and this is the North Pole, because that's where all the magnetic domains are pointing. So if I were to do this, the magnet sticks together. However, I can also flip it and put it like this now, and the magnet sticks together as well because the South Pole and North Pole. So when you break a magnet apart, you end up with two new magnets that both have a North and South Pole. Alrighty, so if you take a look here at this web app, this is from MagLab, you can actually see what happens when you take a bar magnet and you approach a ferromagnetic material. So we have our South Pole here, our North Pole here, and just a piece of iron here. And as the magnet gets closer, you see that the magnetic domains begin to turn, and they align themselves so that their North Pole is pointing to South Pole of the magnet. And the closer the magnet gets, the more these magnetic domains turn and are influenced by the bar magnet. So you can take a moment and read through this article and try out this demonstration to see how all of that works. Alrighty, so at the beginning here, I had this animation of kittens, and I wanted to come back to this because when I think about making a magnet, I think about trying to herd cats. You have to have so many things go just right in order to make it happen. First, you have to have electrons that are in motion and have spin, and those electrons have to be unpaired in an atom so that they don't have canceled magnetic fields. Then those atoms with magnetic fields need to align with each other so that their magnetic field strength is increased and become a magnetic domain. Then you have to align your magnetic domains so that they all face the same direction in order for a ferromagnetic material to become magnetic. And even after you've done all of that, after time, because the atoms are in motion, the magnetic material may end up breaking, or will end up breaking down at a certain point. And that's just like herding kittens. Even if you get them perfectly organized, which takes a lot of effort, it'll still ultimately break out into chaos. Alrighty, folks, go ahead and pause the video, take a 4-question ungraded quiz, and then we are going to go over the answers. All right. Which of the following are properties that cause electrons to be tiny little magnets? Well, we have the fact that they are orbiting the nucleus, they have spin, and they have charge. In order to form a magnetic domain, atoms need to have what? They need to have unpaired electrons, and they need to align their magnetic fields in order to make a stronger magnetic field for the domain. A material such as iron that can be magnetized because it has magnetic domains is a ferromagnetic material. And if you break a magnet in half, what you have now is each piece is now a magnet with both a north and south pole. So if you answer those questions like that, you should have gotten 100%. So folks, if you have questions about magnetic domains or magnetization, please throw them into the discussion questions. I'm going to have a little activity for you tomorrow in our practice about how we make a material magnetic, and then we're going to have a lot of demonstrations on the day after about magnetization in our lesson there. All right.